This video is the first part of section 3.2, which is continuing to deal with bivariate data. Here in this video, we're going to talk specifically about the least squares regression line. This is also the best fit line. So it has a couple different names, but so you have this scatter plot of data. Now we're going to try to fit the best fit line, so the model the data or use a prediction line with the data. All right, our first example in our notes talks about the is wondering whether the age of weightlifters can be used to predict the number of days needed to recover from shoulder surgery. All right, and so we have data for 10 weightlifters. So we have their age and we have the days necessary to recover after surgery. And so I guess it makes sense that we are going to use age, or, the question is actually asking us to use the age of the weightlifter to predict how many days are necessary to recover, with the idea being that if you're younger, it would take fewer days to recover. As you get older, it requires more days to recover. All right. So the first thing we want to do is make sure that we are putting the correct variable on the correct axis, but also that we're labeling that. So the explanatory or x-axis will be age, and the days needed for recovery will be on the y-axis, or is the response variable, and then also, of course, a title. And then we just simply plot each of those points as though it's an ordered pair. So the first weightlifter is 33 years old. It took them 6 days to recover. We plot that point. And so we just continue when we plot all of the 10 points for each of the 10 weightlifters. All right, so in this case, we're giving you the best fit line, the least squares regression line, or the prediction line. Again, these are all sort of synonymous terms. So the regression line or best fit line is y hat equals negative 5.05 plus 0.272x. Remember that the first number here is the y-intercept, and the second number here in the equation, that is our slope. So we can look at this data, and yeah, it's not particularly strong. I would say the correlation is probably going to be pretty low, but here we're concentrating on the best fit line. So if I gave you that equation, could you plot it for us? So our calculators will plot the equations for us. Once we're going to talk today how to do the scatter plot as well in the calculator, but for now let's draw this line in by hand. All right, so the first thing, normally when you draw a line or graph a line, you would use the y-intercept as a kind of a starting point. But notice this x-axis doesn't start at 0, right? 0 would be way down here. And so, as it turns out, we couldn't actually start with the y-intercept. What we would want to do is just plot a couple points. Like we would put 25 in for x and get out the predicted y value. And so we'd plot that point somewhere around here, I think. And then if we had, we put 35 in to x and get that y hat, something probably around here. And then we would take and draw a line between those 2 points. All right, so that is kind of what the best fit line looks like. All right, and so now let's ask some questions. All right, so using the linear equation, what is the predicted number of recovery days for a 16-year-old weightlifter? So go ahead and pause the video while you do that calculation. All right, so if we put 16 in, for our x, then we get kind of what if we think, if we just did this blindly without thinking, we would get kind of a strange result. So it's negative, so that means you would recover before you actually had your surgery, which doesn't make any sense in this context. The issue here is that we are trying to predict using for a 16-year-old, and notice we don't have any data anywhere near a 16-year-old. The lowest we have is, I think, a 26-year-old. So we can't use our model to predict something outside the range of the data that we use to create that model. All right, and so this is called extrapolating, and so we don't want to extrapolate. So that would be on the low end. It doesn't make sense to do it. Also on the high end, so I wouldn't use it to predict the length of time to recover for a 52-year-old either. All right, either end would be bad. All right, so regression lines in general. Again, it summarizes the relationship between those two variables, the explanatory variable and the response variable. We predict the y values from the x values. So we use the explanatory variables to help us try to predict the response variable. We call that predicted y value y hat. So y with a little caret above it, but it's pronounced y hat. And then in statistics, we use a form for the equation that's a little different. So in algebra, we use y equals mx plus b. But for statistics, we use y hat equals a plus bx. A being the y-intercept. Universally in statistics, b is the slope of the equation, of the linear equation. Whereas in algebra, b was always the y-intercept, but not here. Here, b universally is known as the slope. Okay, so the y-intercept, this is the value that the prediction line will take on when the explanatory value is 0. But often that value of 0 makes no sense in the context. It just depends. So for in this case, 0 would mean a newborn weightlifter, a weightlifter that is 0, just born, which doesn't make any sense. So often mathematically the y-intercept might make sense, but in the context of the problem, often it will not. All right, let's show how you would do a scatter plot in your TI-84. Now this is sort of the newer operating system in the 84. You may have an older one, so your screen might look a little different than this. All right, so the first thing you want to do is hit the Stat button. And then you want to type the Edit, but hit the Edit, choose Edit by hitting the Enter button. And then this gives us, takes us to the lists. And what we want to do is we want to put the age data in list 1 and the corresponding days of recovery, number of days of recovery in list 2. But before we get to that, what happens if there's already some old data in one of your lists? Let's talk about how you would clear that out. All right, so we'll use the cursor button to cursor up. You can see right now that the highlighted item in list 1 is the first element or the first cell. So you hit cursor up, and then it highlights, by hitting cursor up, it highlights the name of the list, list 1. And now we will hit the clear button. Don't want to hit delete. It will take away that list. We can bring it back. It's not a problem, but it's complicated. So just hit the clear button and it will clear out the list. Sorry, clear and then enter, and then it will clear out the list. All right, so now we have something that looks like this. Our lists are all empty. Now go ahead and type in the age of each of the weightlifters and the number of days needed to recover. All right, so go ahead and type that in, and then you can always pause this video until you get it all typed in. All right, so now in order to create our scatter plot, hit the second button and then hit the y equals. All right, and that will take us to this screen. And you really want everything to be off right now. Your other two lists, so you have plot 1, plot 2, and plot 3. You have the ability to do 3 plots at the same time. We just want one plot, so we want plot 2 and plot 3 to be off. If necessary, if anything is on, you might just hit 4 and hit enter, and then that would turn them all off, and then hit second y equals again, take us back to this, and it should look like this then. Okay. So we want to select, either hit 1 or hit enter to select plot 1. And then it takes us to this screen here. So the first thing you want to do is turn plot on. So on should be sort of highlighted, and you would hit enter to turn it on. And you can see on is now highlighted. Now you would use the cursor up, down, left, right button to navigate up and down through this screen. We want to choose, we want to go down to the type of graph, and that's the very first one, is the scatter plot. And then you want to make your X list, list 1, and your Y list, list 2. And then once you're finished making those changes, you hit the graph button. When you go to graph, the calculator will show you, probably won't show you the actual graph. It'll show you some part of the XY coordinate plane related to your last graph that you ever graphed. Now, you may never graphed on this calculator if it's new, in which case it'll probably just show you a blank XY coordinate plane. If by just chance your data happens to fall in one of these quadrants, it might show up, but generally speaking, it's not going to. And so there's two ways to do this. We've seen before back in chapter 1 when we did Zoom 9, but let's talk about making our graph just like the one on our paper. So let's hit the window button, in which case we get something like this. Now, your numbers are going to be different than what I'm showing. These are what you want to change the X max, X min, X max all to. So remember, this is what our graph looks like on our paper. And the range of X values will dictate to us what our X min and X max should be. So X min of 25, X max of 35, and then also make sure that your X scale is 1. And then a similar thing for your Y. We go from 0 up to, let's say, 8. And so go from Y min of 0, Y max of 8. And again, the scale there should also be of 1. At which point now we can just hit the graph button and we get our graph. Should look a lot like what we had before. What we had on paper, of course, was on graph paper. So, you had a grid. Also, there's no way that your graphing calculator doesn't display the actual scale on the X or Y axis, that scale that we just set up on the window screen. Okay, so our graph on our paper shows the best fit line, that regression line, the prediction line. And so how can we get our calculators to draw that in for us? Well, there's two ways that we can do it. We can manually type in the equation, or we can get the calculator to store the equation for us. And then either way, when we graph it, it'll show up. So it just graphs it when we ask it to. If we turn on the graph of the line, it's just how the equation gets in is the two different methods. So the first method. All right, so first hit the Y equals button. And then you would just go up to, say, Y1, and you would type the equation in. So this is the equation that we have for this data. And so we would just type in negative. And now you got to be careful. In your calculators, you can't say subtract 5.05. It'll give you an error, so make sure that you are typing a negative sign, not a subtraction sign. It's pretty easy to do that mistake. I've certainly done it before, and I think maybe even I think when I typed this and did a screen capture of my screen, I think that is a subtraction sign because that looks kind of big. So just be careful. You want the smaller negative sign, not the subtraction sign. All right, so we type that in. And then we simply hit the graph button, and then it'll graph the equation. Okay, so just like it is showing up on the last graph of this side of the notes. All right, so there's another method for doing this, and so you don't have to know the equation. When you run the least squares regression, it will take the A and the B, it will take those and it will input the equation for you into y equals. So first, let's go and delete the equation we just put in. So hit the y equals button. And then delete that equation we just typed in, and let's get the calculator to put in the equation for us when we do the regression. All right, so that equation's gone now. And now let's get it to put the equation in for us. All right, so as usual, we're going to do a linear regression. So hit the stat and go over to calculate, and then choose 8, linear regression, a plus bx. And then you want list 1 for your y list, L1 for your x list, and L2 for your y list. And then we want our cursor to be blinking right here. All right, so what we're going to do, it says store regression equation. Do you want to store it somewhere? We haven't done that before, so we've just left it blank. But if we put the variable y1, y sub 1 there, then it will, when it generates the a, the b, the r squared, and the r, it will also just put the equation right into the y sub 1 for us, and that way we don't have to type it in. But we're going to go get the name y sub 1, and when we select it, it's going to paste it exactly where our cursor is currently blinking, which is right there. So make sure your cursor is blinking right there. And then hit the vars button. And then we want to cursor over to yvars. And then you want to choose function. And the first option is y sub 1, so hit 1 or enter. And notice it pastes y sub 1 right there. So it's going to not only run the linear regression, give us our A, our B, and our correlation, but it will also, behind the scenes, plug the equation into y sub 1 so we don't have to actually type it in ourselves. All right, so then go and hit calculate like you normally would. And now nothing really seems to change, right? It looks just the same as we did when we did the linear regression before. But if you hit the y equals button, you see that the prediction equation is in there. And of course, we had negative 5.05, right? It gives it out to, I don't know, 20 decimal places or some ridiculous amount, okay? But essentially it's the same equation. And you can go up here and cursor over if you want to see the rest of these numbers. This is the slope over here. This is the y-intercept, again, out to a ridiculous number of decimal points. And then the slope is over here, the b. All right, so then if we hit the graph button, you'll see that the graph shows up. Now you might have to hit a zoom 9, zoom stats if necessary to get it to show up. And so there you go. That is method 2. All right, so now let's look at an example. The following data It's a little tedious to type this in, but you'll want to type this into your calculator in a second. But the following data is 16 different used F-150 trucks, 16 of them. And so for each truck, we have the mileage and what the truck sold for. Okay, and so I have it plotted there for you, and as well as the best fit line showing up. So you can kind of see that this is a negative relationship, which makes sense. The more mileage the truck has, which is our explanatory variable, the less the truck would be worth, right? The price that you sell it for is less, the more mileage it has. All right, so right now we're going to show how to use your TI-84 to actually find the equation of that best fit line. All right, so we're going to put this data into our TI-84s and have it generate for us the equation of the best fit line. All right, so we'll hit our stat button on our calculator and then select edit. And if there is any data in list 1 and list 2, we need to clear those out. And then we'll go ahead, again, highlight if you need to clear that out, use the cursor button to go up, highlight the title L1, hit clear, do not hit the delete button, hit clear, and then enter. And then you do the same thing with L2, cursor to the right, cursor up, highlight L2, hit the clear button, and hit enter, and that will clear those out. All right, so hitting the delete button, if you accidentally hit the delete button, it deletes the entire list. So L1 disappears. It doesn't really delete it, it just kind of hides it from view, and you can pull it back, or if you can't figure out how to do it, I can certainly show you how. But you don't want to hit the delete button when you're trying to clear out the list. You want to hit the clear button. All right, so once you have that data, those lists cleared out, then go back to L1 and type in all 16 data values, and then go into L2 and type in all 16. Let's see, L1 will be the mileage, and L2 will be the price of that the truck sold for. Make sure that those two numbers next to each other in our list are from the same corresponding truck. So in other words, if I accidentally forgot to type this number in, all of these numbers would be shifted up one, and we'd have the wrong numbers the wrong prices next to the wrong mileage. So it's really important. You can't just like, oh, I skipped one, I'll put it in at the end. That doesn't work. You have to have, the computer must have the mileage for a truck next to that truck's price that it was sold for. All right, so pause this video and then put all that data in, and then we're going to use this data over the next couple of days. So if you're doing homework tonight, I would recommend using list 3 or list 4 for your homework. You really want to leave this truck data in your calculators for the next couple of days. All right, so you've got that data in. If not, pause and then come back to the video once you have it in. But you have that data in, and then you hit the stat button, and then you cursor over to calculate, and then you want to scroll down. Now, there are 2 different linear regression options here. One is linear regression AX plus B. That is what you would use if we were in an algebra class. AX plus B, or really MX plus B, B being the y-intercept in algebra. Here in statistics, we want to go down to choice 8, which is linear regression A plus BX. In statistics, B universally is known as the slope of the least squares regression line, not the y-intercept. So at this point, you can either hit 8 or scroll down to 8 and then hit enter. All right, then you get something like this, and it's asking you where your X list is and where your Y list is. You want to choose your X list is list 1, your explanatory variable is in list 1. Your y, or response variable, is in list 2. All right. I don't know if anyone has a TI-83 this year, or if you have an older 84 operating system. Sometimes this screen doesn't show up in the older operating systems. So if that's the case, then what happens when you choose number 8 here on the stat calc, and you choose 8, it puts this on the home screen, lin regret a plus bx. And now what you'd want to do is just type L1, comma, L2, and then hit enter if you have the older operating system. Again, if you have the older operating system, you don't have this user interface screen here. All right, that's for the TI-83. So you would do, it would give you lin regret a plus bx, and then the cursor would be, just blinking right here. Type L1, and then hit comma, and then type L2. And L1 and L2 are arrived at by hitting second and 1, comma, second, and then 2. Gives you L1 and L2. All right, so one way or another, you end up getting to this screen here. And so it gives us the A and the B for our least squares regression equation. This is really y hat. It just puts it as y, but it's really y hat. And then your correlation is here. And then also something called the coefficient of determination, or R squared, is also given to us there. We'll talk about that more at a later date. All right, so so the A and the B are the A and the B in our least squares regression. So you pull those things out, and you just simply add them to our equation. We would round to here I rounded to 5 places. All right, so now what we want to do is use that equation to estimate the price that you would pay for an F-150 truck that has been driven 100,000 miles. What would you predict that price to be? All right, so we will put the 100,000 in for our X, or our explanatory variable, and calculate that. And it's about $21,965 is what you would expect to pay. All right, what would someone pay you for an F-150 truck that has 300,000 miles? Calculate that one. All right, so again, we put 300,000 in. You can recall the previous calculation in your calculator and just change the 1 in 100,000 to 3. It's a little faster. But that ends up giving us negative $10,619. But it's negative, right? So that means they're not going to pay me. I would end up paying them to take that truck, which doesn't really make sense, right? Even if it's not really worth that much, I certainly would not be paying someone $10,000, more than $10,000, to take the truck off my hands. So this is an example of extrapolating. If you look back at our data, we don't have a single truck whose mileage is anywhere near 300,000. So this would be an example of extrapolation, and it often, when you extrapolate, it gives you sort of bizarre answers. In this case, yeah, that you would have to pay someone. If you're giving them your car, you would give them the car and also have to pay them nearly $11,000, which wouldn't make sense. All right, so here's another example. Some data were collected on the weight of male white lab rats for the first 25 weeks after their birth. A scatter plot of the weights in grams and the time since birth in weeks shows a fairly strong positive relationship. The linear regression equation, they give that to us. So instead of saying y hat, the response variable is weight, and so we'll put a little hat caret or hat over the weight. So the predicted weight is equal to 100 plus 40 times the time, and that's of course in weeks. And that models the data fairly well. First question, what is the slope of the regression line? And explain what it means in context. So pause the data, pause the video and answer that question, and then unpause it. All right, so the slope is just that 40. The units are grams per week. And what does that mean? It means for every increase in 1 unit of the explanatory variable, we would expect an increase in 40 grams of the response variable. So that means that for every increase in 1 week of time since birth, we would expect the rat to gain 40 grams in weight. All right, number 2, what is the y-intercept? Explain what it means in context. Is the y-intercept statistically significant here? In other words, does it make sense in context here? All right, so what is the y-intercept? In this case, the y-intercept is 100. And that just means that, what does it mean? The y-intercept occurs when the explanatory variable is 0, so that means the rat is born. And so at the moment the rat is born, time is 0, and we would expect that weight to be 100. And it does make sense here because the data goes all the way back down to time since birth, and so it's not extrapolating here. It does make sense in context. All right, it's simply the weight of a newborn rat. All right, number 3, predict a rat's weight when it is 16 years old. All right, so do that, pause the video. All right, so we've simply plugged that into the equation. We put 16 in for the explanatory or x variable into the equation up here, into time. And that gives us 740 grams. All right, now predict, number 4, predict the rat's weight when it is 2 years old. Remember here that time is in weeks. So pause the video and calculate that one. All right, so the data, remember that the data is from the time of birth up to 25 weeks. 2 years is 52 weeks in a year, so 104 weeks is way outside the range of our data. Our data is within 25 weeks, so this is, as it turns out, 4,260 grams, or roughly, because I told you how many pounds are in a gram, that's about 9.4 grams. That's about the size of a small turkey. So hopefully we wouldn't encounter a rat that is almost 10 pounds heavy. So this again is extrapolating. We would not want to extrapolate here. It gives us unreliable results. All right, so we have homework due next class. Remember too that this really just means that this 3.35 means problem number 35 in chapter 3. That's what the 3 means. Remember that you won't actually find a homework problem called 3.35. If you look in the back of the book for answers, though, they will be listed using this kind of a format as far as the question goes. And so this homework is due next class.